Let's review the now familiar definition of sequential consistency. It says that the result of any execution is the same as if the memory operations of all processors were executed in some sequential order and the operations of each individual processor appear in this sequence in the order specified by its program. When students learn about sequential consistency, they sometimes think it means that all writes are instantly visible everywhere in the system. That, of course, is impossible to implement, the speed of light being what it is, and so that's not what it means. We can take a look at a couple of sequentially consistent actions, one of which appears that it might not be what sequential consistency requires, but on further examination it turns out that it's just fine. This example uses a diagram that I will call a Tannenbaum diagram after Andrew Tannenbaum, who invented it. And it shows what happens in each processor at which time. So the processors are listed one above the other, and time proceeds from left to right. In this diagram, processor 1 writes a value 1 to location X at this time, and then later on processor 2 reads from the same location from X and fetches a 0, and then later it reads from X and fetches a 1. Now remember, we said that sequential consistency doesn't require that writes be seen instantly throughout the system. And in fact, the write by P1 takes a while to propagate to P2. But this is still sequentially consistent because global writes are still seen in order. There's actually only one global write here, and that's WX1, and it's seen at this time in P1, and it's seen in that time at P2. If we had more global writes, they would have to be seen in the same order throughout the system, but we don't, so this is kind of by default sequentially consistent, despite the fact that the write to location X is not seen instantly by P2. Now, we have another diagram over here that illustrates the same thing. Here processor 1 writes a 1 to location X, and processor 2 does a read just after that, and it fetches the value of 1. These two are both sequentially consistent. Sequential consistency doesn't require instantaneousness. It just requires that shared writes be seen in the same order throughout the system, and that memory operations from any particular processor appear in the order that they do in its program, in that overall order. So that's sequential consistency. The next kind of consistency we want to look at is causal consistency. And with causal consistency, we distinguish between events that are causally related and those that are not. Events that are causally related need to be seen in order, but those that are not are just considered to be concurrent, and it doesn't matter what order they're seen in. Two events are said to be causally related if one can influence the other. So our first example here is processor 1 writing a 1 to location X, and then processor 2 reading from location X and fetching a 1, and then writing a value of 2 to location Y. Here, the write to X could influence the write to Y. Think about why. Because P2 read X, and it could have used the value of X in the calculation of Y. On the other hand, if that read of X was not there, then the two writes would not have been causally related, because there's no way that the information that was written to X over here can flow to the write that takes place over there. The following pairs of operations are potentially causally related. A read followed by a later write by the same processor, because a processor could have read a value and used it to calculate the value that it wrote. A write followed by a later read to the same location, because the value written was fetched when the later read occurred. And also the transitive closure of these two types of pairs of operations are causally related, because the causal chain runs between each two operations in the list. And so the first one is related causally to the last one. Operations that are not causally related are said to be concurrent. The definition of causal consistency says that writes that are potentially causally related need to be seen in the same order by all processors, but other writes are said to be concurrent, and it doesn't matter what order they're seen in. Here's a sequence of events that's allowed with a causally consistent memory but disallowed with a sequentially consistent memory. So we see that processor 1 writes the value 1 to location X, and then processor 2 reads the value of 1 from location X. In fact, processors 2, 3, and 4 read the value of 1 from location X. And then after all those other processors read the value of X, processor 1 changes X to 3, and processor 2 changes X to 2. And then processor 3 goes ahead and does a read to location X, and it gets a 3, which is the first value that was written after all those reads took place. And then later it does another read of location X and gets 2. Whereas P4 does a read of location X and gets 2, and then later on it does a read of location X and gets 3. Now this isn't going to be allowed by sequential consistency, and I think you can see why. Because the later two writes to location X, the write of 3 by processor 1 and the write of 2 by processor 2, are seen in a different order by P3 and P4. P3 sees the 1 by P1 first and the 1 by P2 second, and P4 sees them in the opposite order. But this is allowed by causal consistency. And the reason for that is that these two writes, the write of 3 to location X and the write of 2 to location X, are not causally related. That is, processor 2 doesn't read the value of 3 and then use it to compute 2 or vice versa. So because of the fact they're not causally related, they're considered to be concurrent, and they can be seen in any order. In other words, the system doesn't have to keep these two writes in order as seen by the other processors. Now let's take another sequence here where P1 writes 1 to X, and P2 reads X and gets 1, and then it writes 2 to X. And P3 reads X and gets 2, and then later reads X and gets 1. And P4 gets the values in the reverse order. So what's the violation of causal consistency? Well, the violation is that these two writes are causally related, because P2 reads the value of X that's written there and could potentially use it to compute the value of X that it writes right there. So those two writes need to be seen in order by all processors. If we didn't have this read there, then we have two writes that were not causally related, and it would be okay for them to be seen in different orders by processors P3 and P4. It's not trivial to implement causal consistency. It requires the construction of a dependency graph, and I won't go through how that's done, but it is quite feasible to do it. It's just not straightforward. That shows which operations depend on other operations, but nonetheless, causal consistency saves time because a processor can write a local copy of the variable and continue without waiting for that write to reach the farthest end of the network. You know, any write that it's not causally related to doesn't have to be seen in order with it, so the processor that does the write doesn't have to wait unless there's another causally related write that it's doing. So this helps in achieving concurrency, but it does so at the cost of some complexity in implementation.